myself, Hiren Patel, associated with LJ Institute of Engineering and Technology. So, in last video, we have started the first chapter of Physics Group 1, that is Properties of Matter. Till now, we have learned that what is elasticity, concept of load and its classification, concept of stress and different types of stresses, and different type of strain, along with Hooke's law. Now, in this video, we will learn the topic such as stress-strain diagram, which is also known as relationship between stress and strain. Also, few properties of material such as ductility, brittleness and plasticity, along with working stress and factor of safety. So let's start with the first topic of today's session, that is stress-strain curve. So as you can see in the figure, there is a graph of stress versus strain. So the relationship between stress and strain is also known as stress-strain diagram. So following are the salient points on this curve. So let's start with the first point, that is limit of proportionality. So you can see in the figure, in the range OA, the strain is directly proportional to the stress, or we can say that load. So here the graph is a straight line. So we can say that point A is limit of proportionality, because in this range between O to A, strain is directly proportional to the stress. So it is the value of stress up to which strain and stress has a constant ratio. We can say that it obeys Hooke's law. So now the second point is elastic limit. So you can see in the figure, at point A, the curve deviates from the straight line and the graph from A to B is non-linear. So if the load is increased beyond A up to B, the material behaves in elastic manner, means on the removal of load, the whole deformation will vanish. So we can say that this is the point up to which it obeys the elastic properties. So the value of stress corresponding to this point B, up to which the material behaves in an elastic manner, is called the elastic limit. Again, I repeat that important point, that if the load is increased beyond A up to B, the material behaves in elastic manner, means on the removal of load, the whole deformation will vanish. So we can say that the value of stress corresponding to the point B, up to which the material behaves in an elastic manner, is called elastic limit. So up to point B, the material will be in elastic range, and beyond B, it will be in a plastic range. So we can say that after point B, material will lose its elastic properties. So now, the third point, at point C, you can see in the figure, the point C is called as upper yield point. So at this point, there is an increase in strain, even though there is no increase in stress. So the value of stress corresponding to point C is called yield stress. So yield stress is defined as that unit stress which will cause an increase in length without an increase in load. Here, yield stress is also defined as that unit stress which will cause an increase in length without an increase in load. So now we know that at point C there is an increase in strain even though there is no increase in stress. That's why this stress is also known as yield stress and point C is known as upper yield point. So now, moving further, you can see in the figure at point D, it is also known as lower yield point. So after yielding reached at D, further stress and strain can be obtained by increasing the load. So we can say that at point D, we can achieve a stress and strain so that point D is also known as lower yield point. Now, moving further towards this graph, after increasing the load beyond the yield point, the stress strain curve rises till point E is reached. That point is also known as ultimate load point. So keep in mind that after point D, by increasing the load beyond the yielding point, the stress strain curve rises till point E is reached. So this point is also known as ultimate load point. So the stress corresponding to this point is maximum and it is also known as ultimate stress. Because at this point the stress is maximum. So at this stage, cross-section area at particular section reducing very fast, and this is called neck formation. You can see in the figure, at this stage the area of particular section reducing very fast. So this is called neck formation. So keep in mind that after increasing the load beyond the yield point, stress strain curve rises till the point E is achieved, and that point E is known as ultimate load point. Now, next is breaking load point. So up to point E, cross-sectional area goes on decreasing, forming a neck, as we have discussed in earlier point. So this cross-section area becomes smaller and smaller. If now the specimen is broken at F into the two pieces, so we can say that at point F the sample is broken. That's why that point F is called as breaking load point, and the stress corresponding this point F is known as breaking stress of material. So here in this stress strain diagram we have discussed about the first point, that is elastic limit. Next is upper yield point, then lower yield point. At point D it is lower yield point. After that at point E, that is ultimate load point, and last at point F we can say that is breaking point, and the stress related to that point is known as breaking stress of material. So this is all about stress strain diagram. Now we will move further to the next property. So we will start with the first property of material, that is ductility. So if a deforming force is applied on a material and it acquires a large permanent deformation without producing any fracture, then that material is said to be ductile, and the property is known as ductility. So I repeat that statement. If a deforming force is applied on a material and it acquires a large permanent deformation without producing any fracture, then that material is said to be ductile, and this property is known as ductility. So we can see here that breaking point for a ductile material will be very much above the yield point, as we have discussed in state diagram. Also, ductility can be measured in terms of percentage elongation. So higher the percentage elongation, more the ductile material is. So we can say that a body possessing ductility can be reduced from a large section to thinner section. It means that it can be drawn into the wires. So silvers, coppers, aluminiums are ductile materials because we can make many electrical wires from that materials because it has a ductile property. So it is about the ductility. Now next is brittleness. So it is opposite to the ductility. A brittle substance fractures without any appreciable amount of permanent deformation. So we can say that it is opposite to the ductile property. Again, a brittle substance fractures without any appreciable amount of permanent deformation. So stress strain curve of brittle material hardly shows any yield point and normally coincide with the breaking point. So we can say that from that stress strain diagram of brittle material, or we can say that material which possesses brittleness, it hardly shows any yield point, and normally in that diagram that yield point coincides with the breaking point. So all non-ductile materials are brittle. Compression test is generally performed for testing brittleness of material. So it is a compressive quality of material. So this is about brittleness. Again I repeat the important terms related to their properties. So brittleness is opposite to the ductility. A brittle substance fractures without any appreciable amount of permanent deformation. So we can say that stress strain curve of brittle material hardly shows any yield point and it normally coincides with the breaking point. Now we will move further to the plasticity. So the materials are capable of getting deformed permanently without producing any fracture. So this property is known as plasticity, and the materials which possesses that type of property is known as plastic material. So here I repeat that property, that some materials are capable of getting deformed permanently without producing any fracture. So this property is known as plasticity. So we can say that lack of elasticity is also known as plasticity. Now the next point which we are going to discuss is working stress. So maximum stress applied on a given material within its elastic limit is known as working stress. So we can say that here the load corresponding to that process is also known as working load. So basically working stress is nothing but the ratio of actual axial load to original cross section area. So you can see in the slide that working stress is equal to actual axial load upon original cross section area. So for the safety of structure, it is essential that working stress should be within elastic limit of material. Otherwise, that material can be break at some moment. So, this is working stress. So, maximum stress applied on a given material within its elastic limit is called working stress. Now, the next property is factor of safety. The ratio of breaking stress to working stress is known as factor of safety. Now, we are aware of both these terms, breaking stress and working stress. Working stress must be within its elastic limit. So here, factor of safety is also defined as ratio of breaking stress to working stress. Here, there are different factors that affect that factor of safety. So, that factor of safety depends on the type of material, behavior of material under different loading conditions, effect of physical conditions such as temperature, environment, etc. And last but not the least, that is safety of user. So these are the factors that affect the factor of safety. So this is all about today's session. So in this session, we have discussed about the very important theory, that is stress-strain diagram. We have discussed various points on that stress-strain curve. Then we have discussed ductility, brittleness and plasticity. And also at last we have discussed working stress and factor of safety. So now in the next video we will learn elastic behavior of solids, factors affecting elasticity, types of elasticity and various types of elastic modulus. So that's it for today's session. Thanks for watching.